There's something unsettling and utterly exhilarating about staring into the night sky and realizing how little we truly understand. For centuries, we've mapped constellations, tracked planets, and pieced together the laws of physics, convinced we were unraveling the universe's secrets. But what if everything we thought we knew is just the tip of an iceberg so vast it defies comprehension? Right now, astronomers and physicists are uncovering cosmic mysteries so profound they're not just rewriting textbooks, they're reshaping reality itself. Imagine a force so powerful it's tearing the universe apart at the seams, or black holes so bizarre they challenge the very fabric of space and time. These aren't plot twists from a science fiction novel, they're real, groundbreaking discoveries happening right above our heads. Think about the last time you felt that spine-tingling awe under a starry sky. That sense of wonder is more than just nostalgia. It's a reminder that the universe is alive with questions waiting to be answered. Dark energy, an invisible force pushing galaxies apart faster than light, wasn't even on our radar 30 years ago. Now it's one of the greatest enigmas in science, hinting at dimensions and forces beyond our wildest theories. And black holes, these cosmic devourers, aren't just vacuuming up stars. They're bending the rules of physics, warping time, and possibly holding clues to entirely new universes. The more we learn, the clearer it becomes. The cosmos is far stranger, far more dynamic than we ever dared to dream. This isn't just about distant galaxies or abstract equations. These revelations ripple into our everyday lives, challenging how we see ourselves in the grand tapestry of existence. If dark energy controls the fate of the universe, what does that mean for our place in it? If black holes can erase information, does reality itself have cracks in its foundation? Today, we're diving into the most startling cosmic discoveries that are turning science upside down, from the eerie whispers of gravitational waves to the mind-bending possibility of parallel worlds. By the end of this journey, you won't just see the night sky differently. You'll feel it, a humbling reminder that the universe is still writing its story, and we're lucky enough to witness it unfold. The idea that the universe is expanding isn't new, but the realization that it's doing so faster and faster, that sent shockwaves through the scientific community. Picture a balloon being inflated, but instead of slowing down as it stretches, someone suddenly starts pumping air into it with reckless abandon. That's essentially what dark energy is doing to our cosmos. This mysterious force, invisible and undetectable by conventional means, isn't just a passive backdrop of space, it's an active player, relentlessly driving galaxies apart. And here's the kicker, we have no idea what it actually is. One leading theory suggests dark energy could be Einstein's cosmological constant, a kind of energy woven into the fabric of space itself. Einstein originally proposed it to explain a static universe, then famously called it his greatest blunder when the expanding universe was discovered. But now it might be staging a comeback, another wild possibility. Empty space isn't really empty. Quantum physics tells us that even a vacuum crackles with fleeting particles popping in and out of existence. Could these tiny fluctuations be generating enough energy to push the universe apart? The math hints at it, but the numbers don't quite add up, leaving scientists scratching their heads. Then there's the most dramatic scenario, the Big Rip. If dark energy grows stronger over time, it could eventually overpower gravity, electromagnetism, even the forces holding atoms together. Galaxies would be shredded first, then stars, planets, and finally, in a split second, every molecule in existence. It sounds like something from a doomsday prophecy, but it's a real theoretical outcome. And if that's where we're headed, the countdown isn't just ticking for stars and galaxies, it's ticking for the very laws of physics as we know them. What makes dark energy so baffling isn't just its power, but its timing. For billions of years, gravity dominated, slowing the expansion. Then, around 5 billion years ago, dark energy took the wheel. Why then? Was it a cosmic switch flipping or part of some deeper, unseen mechanism? Every answer we find only leads to more questions, revealing just how much of the universe remains hidden in plain sight. One thing's certain: the fate of everything from distant quasars to the phone in your hand hinges on forces we're only beginning to glimpse. Black holes have long been painted as the ultimate cosmic predators, silent, ravenous monsters lurking in the void, swallowing everything that crosses their path. But what if we've had it all wrong? Stephen Hawking turned that terrifying image on its head when he revealed that black holes aren't just consuming the universe, they're leaking. That's right, these gravitational giants slowly emit radiation, fading away like ice melting in the sun. This phenomenon, now called Hawking radiation, was a bombshell. It meant black holes aren't eternal prisons after all. Given enough time, they'll vanish in a whisper of particles, leaving behind nothing but empty space. How does this even work? Picture the edge of a black hole, where gravity is so intense that not even light can escape. According to quantum physics, pairs of particles constantly flicker into existence near this boundary. One falls in, while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over billions of years, this slow leak adds up, shrinking the black hole until it finally winks out of existence. It's a cosmic balancing act between gravity and quantum weirdness, proving that even the universe's darkest corners play by unexpected rules. But Hawking's revelation was just the beginning. Some physicists now speculate that black holes might be more than just traps. They could be portals. The math suggests that at their cores, the laws of physics break down entirely, opening the door to wild possibilities. Could a black hole's crushing interior lead to another universe, a parallel reality with its own stars, galaxies, and perhaps even life? Or might they contain hidden dimensions, folded layers of space-time we can't yet perceive? These aren't just sci-fi fantasies, they're serious theories debated in labs and lecture halls worldwide. What's truly mind-bending is how black holes blur the line between destruction and creation. When a star collapses into one, does its information simply vanish? Quantum mechanics says no information can't be destroyed. So where does it go? Some scientists argue it's encoded in the Hawking radiation, scrambled but still there. Others propose it's ejected into another universe entirely. Either way, black holes are rewriting the rules, forcing us to question whether anything in the cosmos truly disappears, or if it's all just transformed in ways we're only beginning to grasp. The more we learn, the clearer it becomes. Black holes aren't the end of the story. They're puzzles wrapped in enigmas, cosmic laboratories where the universe tests its most extreme ideas. And with every discovery, they remind us that reality is far stranger, far more inventive than we ever dreamed. Dark matter is the universe's silent architect, shaping everything from the smallest galaxies to the largest cosmic webs. Yet we've never seen it, never touched it, never directly detected it. Imagine building a house where 85% of the materials are invisible, yet without them, the entire structure would collapse. That's the role dark matter plays in our cosmos. Its gravitational pull is the glue holding galaxies together, keeping stars from flying apart as they spin. Without it, the Milky Way would unravel like a snapped rubber band, scattering stars into the void. For decades, scientists have been chasing shadows, searching for something that refuses to be seen. underground labs shielded from cosmic noise, house detectors waiting for the faintest tick of a dark matter particle colliding with ordinary atoms. Out in space, telescopes map the distortions of light caused by dark matter's gravity, tracing its hidden fingerprints across the sky. But so far, every experiment has come up empty. The leading candidate, a hypothetical particle called a WIMP, weakly interacting massive particle, remains elusive, leaving researchers to wonder if they're hunting a ghost. Could dark matter be something even stranger? Some theories suggest it might not be a particle at all, but a cosmic illusion. Modified Newtonian dynamics, or MUND, proposes that our understanding of gravity is incomplete, that on galactic scales, gravity behaves differently than Einstein's equations predict. It's a radical idea, one that would upend a century of physics. But here's the catch. While MUND explains some galactic rotations, it falters when applied to galaxy clusters, leaving dark matter as the stronger contender. Then there's the possibility that dark matter isn't uniform. Some models suggest it forms dense streams or dark matter hurricanes sweeping through the galaxy, while others propose it could interact with itself through unknown forces, creating invisible structures within structures. Recent observations of galaxies with no dark matter at all have only deepened the mystery. How can some galaxies lack the very ingredient thought to be essential for their existence? The stakes couldn't be higher. Dark matter isn't just a cosmic curiosity, it's the scaffolding of reality. If we solve its riddle, we might uncover entirely new laws of physics, or even glimpse hidden dimensions. Until then, it remains the universe's most frustratingly absent presence, a reminder that what we don't know still far outweighs what we do. And as long as it lingers in the shadows, our picture of the cosmos will remain tantalizingly incomplete. Multiverse theory shatters the comforting notion that our universe is all there is. Picture standing in front of a mirror, only instead of seeing a single reflection, the glass splits into endless versions, each showing a slightly different reality. That's the essence of the multiverse, not just one cosmos, but a sprawling, perhaps infinite collection of universes, each with its own unique rules. Some might have stronger gravity, making stars burn out faster. Others could lack the forces that bind atoms, rendering life impossible. And in a startling twist, a handful might be nearly identical to ours, with alternate versions of you reading these very words in a slightly different way. This idea isn't just philosophical speculation, cosmic inflation, the theory that our universe expanded exponentially in its first moments, suggests that this rapid stretching could have created bubble universes, each pinching off into its own isolated spacetime. String theory takes it further, proposing that higher dimensions beyond our four might harbor parallel worlds, separated by membranes thinner than a whisper. Even quantum mechanics hints at branching realities where every decision spawns new timelines. The evidence is indirect, like catching shadows on a cave wall, but the math refuses to let the idea go. What does this mean for our place in the cosmos? If countless universes exist, ours might not be special, just statistically inevitable. Think of rolling a die an infinite number of times. Eventually, you'll land on every possible combination. In a multiverse, a universe with the perfect conditions for life becomes unavoidable, no divine fine-tuning required. But here's the haunting flip side. If life can emerge elsewhere in the multiverse, why does space here feel so empty? Where are the other civilizations? Some universes might be teeming with intelligence, while ours, by sheer chance, is a quiet outlier, the most provocative possibility. That we'll never know for sure. Parallel universes, by definition, might be forever beyond our reach, their light never crossing into our cosmic horizon. Yet the mere idea reshapes how we see reality. If the multiverse is real, then every star, every galaxy, every law of physics we cling to might be just one variation in an unimaginable symphony of existence. A humbling reminder that the universe, or universes, still hold mysteries we've only begun to ponder. Einstein's theory of relativity didn't just change our understanding of space, it shattered our perception of time itself. Picture a clock ticking steadily on Earth while another races ahead on a speeding spacecraft. To an astronaut, time feels normal, but back on the ground, their watch would appear to crawl. This isn't science fiction, it's time dilation in action, a proven phenomenon where gravity and velocity stretch or compress time like taffy. Even your phone's GPS relies on this. Satellites orbiting Earth experience time slightly faster than we do down here, and without constant corrections, navigation systems would misplace you by miles within minutes. But the real cosmic curveball comes when we push relativity to its limits. Near a black hole where gravity twists spacetime into knots, time doesn't just slow, it grinds to a near halt. Imagine watching a spaceship spiral toward the event horizon. From your safe distance, you'd see its crew moving in agonizing slow motion, their signals stretching into deeper and deeper red shifts. For them, though, minutes might pass before catastrophe strikes, while centuries fly by elsewhere in the universe. It's a one-way ticket to the future with no return trip in sight. Could we harness this for time travel? The math says maybe. A Tipler cylinder, a hypothetical structure spinning at nearly light speed, could warp spacetime into a loop, allowing you to circle back to your own past. Wormholes, cosmic shortcuts through folded space, might offer another route if they exist and don't collapse instantly. But here's the catch. These ideas demand energies and materials beyond our reach, like exotic matter with negative mass. Even if possible, the universe might enforce its own paradox police. Step on a butterfly in the past, and quantum mechanics could rewrite history to stop you before you even left. The most haunting question isn't how to manipulate time, but what its fluidity reveals about reality. If time can stretch and bend, is it truly fundamental, or just an illusion woven from deeper physics? Some theorists argue time emerges from the quantum entanglement of particles, like a movie projected from countless tiny interactions. Others propose it might not exist at all outside our perception, a cosmic sleight of hand to make the universe comprehensible. One thing's certain, relativity keeps humbling us. The faster we go, the more time warps. The closer we get to a black hole, the more the rules twist. And somewhere out there, in the universe's quiet corners, time itself might be standing still, frozen in a gravitational vise. These aren't just abstract quirks, they're reminders that the fabric of reality is far more malleable, far more mysterious than our everyday experience suggests. Quantum entanglement is the universe's ultimate magic trick, particles so deeply linked that changing one instantly alters its partner, no matter how far apart they are. Picture tossing two coins into opposite sides of the galaxy, only to find they always land on the same face every single time. Einstein famously dismissed this as spooky action at a distance, convinced it violated relativity's cosmic speed limit. Nothing can outrace light. Yet decades of experiments have proven entanglement is real, leaving physicists both exhilarated and unnerved. How can particles communicate faster than a photon can blink? The answer might lie in rewriting our understanding of reality itself. At the heart of entanglement is a bizarre quantum property called superposition, where particles exist in multiple states at once until measured. Imagine a spinning top that's simultaneously rotating clockwise and counter-clockwise. Only when you touch it does it choose a direction. Entangled particles take this further. Their states are intertwined, so observing one instantly sets the other's state, even if it's light years away. It's as if the universe keeps a hidden ledger, ensuring the books always balance, no matter the distance. This isn't just theoretical sleight of hand. Labs worldwide are harnessing entanglement to build quantum networks where information leaps between particles with unhackable security. Traditional encryption relies on math problems that would take centuries to crack. Quantum keys, though, self-destruct if intercepted, thanks to entanglement's delicate nature. Then there's quantum computing, where entangled qubits perform calculations at speeds that would make today's supercomputers look like abacuses, a problem that might take millennia to solve. A quantum machine could crack it in minutes, but the how remains a mystery. One radical idea suggests entangled particles aren't truly separate. They're threads in a deeper fabric of reality, like shadows cast by a single, hidden object. String theory hints that higher dimensions could tether them in ways our 3D brains can't visualize. Others propose the universe is fundamentally non-local, meaning distance is an illusion at the quantum level. Even more mind-bending is the many worlds interpretation. What if the particles aren't communicating at all, but every possible outcome plays out across branching realities, and we're just seeing one slice? The implications rattle the foundations of physics. If entanglement defies locality, the idea that objects are only influenced by their immediate surroundings, then space itself might be a kind of hologram, a projection of deeper laws. Some experiments even suggest time might emerge from entanglement, with particles remembering their connection across epochs. It's as if the universe runs on invisible threads, stitching together everything from atoms to galaxies in a web we're only beginning to trace. Perhaps the most humbling thought, entanglement might be everywhere, woven into the fabric of existence. The same phenomenon that powers quantum computers could underpin the chemistry of life, the formation of stars, even the flow of time. We've spent centuries dissecting the universe into smaller and smaller pieces, only to find that at the most fundamental level, everything is connected instantly, irrevocably, and in ways we're only starting to dream of. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars, many hosting planets just like Earth. Given those numbers, the cosmos should be teeming with life. So why does the night sky feel so eerily empty? This is the Fermi Paradox, a question that haunts astronomers and philosophers alike. If the conditions for life are so common, where is everybody? The silence is deafening, and the explanations are as unsettling as they are fascinating. One chilling possibility is that advanced civilizations inevitably self-destruct. Imagine a species harnessing the power of nuclear fusion, artificial intelligence, or nanotechnology, only to turn those tools against themselves. War, environmental collapse, or runaway technology could act as a cosmic filter, wiping out civilizations before they ever reach the stars. If that's the case, the reason we haven't heard from aliens is tragically simple: they no longer exist. Then there's the zoo hypothesis, the idea that intelligent life knows we're here but chooses not to interfere. Picture humanity as an ant colony under observation, studied from a distance by beings so advanced we're barely worth contacting. Or perhaps interstellar travel is far more difficult than we imagine, with physical barriers like the speed of light keeping civilizations isolated. Even if aliens exist, they might be trapped in their own solar systems just like us. But what if the answer is simpler still? Earth could be a fluke, a one-in-a-trillion accident where everything aligned just right. The right star, the right distance, the right moon to stabilize our climate. Maybe the universe is overwhelmingly hostile to life, and we're the exception, not the rule. New telescopes like the James Webb Space Telescope are scanning distant atmospheres for signs of oxygen, methane, or industrial pollution, hints of life, or even intelligence. Yet every silent night sky serves as a humbling reminder. Either we're alone or we're missing something fundamental about the universe. Until we know for sure, the Fermi Paradox remains a haunting riddle echoing through the void. Neutron stars are the universe's ultimate alchemists, cosmic furnaces where matter is squeezed so tightly that a teaspoon of their material would weigh 1 billion tons. Now imagine two of these ultra-dense remnants of dead stars spiraling toward each other, locked in a gravitational dance that ends in catastrophe. When they finally collide, the explosion is so violent it ripples spacetime itself, sending gravitational waves echoing across the cosmos. But that's not all. In the wreckage of this collision, something extraordinary happens. Atoms are crushed together with such force that they forge gold, platinum, and other precious metals, enough to litter entire galaxies with riches. This phenomenon, known as a kilonova, isn't just a dazzling light show. It's the answer to one of Earth's oldest mysteries. Where did our planet's gold come from? The jewelry on your finger, the circuitry in your phone, none of it would exist without these cataclysmic mergers. Unlike ordinary supernova, which create lighter elements like carbon and oxygen, kilonovae are the universe's exclusive workshops for heavy metals. The collision's insane pressure and neutron-rich environment fuse atomic nuclei into elements so dense they'd sink through Earth's crust like stones in water. But the real magic lies in what these collisions reveal about the extremes of physics. For a split second, conditions inside the merger reach temperatures 1 million times hotter than the sun's core, warping spacetime so severely that time itself would slow to a crawl for any hypothetical observer. Matter is stretched and twisted into bizarre shapes, possibly even forming exotic states we've never encountered, like quark-gluon plasma, a primordial soup that hasn't existed since the Big Bang. Some theories suggest these events might briefly create strange matter, a hypothetical substance so stable it could convert everything it touches into more of itself. The first confirmed neutron star collision, detected in 2017, was a watershed moment. Gravitational wave observatories and telescopes around the world caught the aftermath in real time, watching as the glow of radioactive heavy metals lit up the sky. The data matched predictions almost perfectly, confirming that these mergers are cosmic gold factories. Yet, for all we've learned, the full picture remains elusive. Could these explosions also produce elements beyond our periodic table? Are there forms of matter lurking in their debris that defy our current laws of physics? Every kilonova is a Rosetta Stone for decoding the universe's most extreme environments. They're natural laboratories where gravity, quantum mechanics, and nuclear physics collide in ways we can't replicate on Earth. And with each new detection, we're not just uncovering the origins of precious metals, we're peering into a realm where the rules of reality itself are rewritten. Imagine a world where the rain isn't made of water, but diamonds, or a planet so close to its star that its skies rain molten glass, scattering light like a shattered prism. These aren't scenes from a fantasy novel. They're real exoplanets, worlds beyond our solar system that defy every expectation. Since the first confirmed discovery in the 1990s, astronomers have catalogued thousands of these alien worlds, each one rewriting the rules of what a planet can be. Take WASP-76b, a gas giant where temperatures soar so high that iron vaporizes on the day side, only to condense and rain down as molten metal on the night side. Or HD 189733b, a cobalt blue world lashed by supersonic winds carrying droplets of molten glass. These aren't just scientific curiosities, they're windows into the universe's boundless creativity. But the real game changers are the planets orbiting in the Goldilocks zone, the region around a star where temperatures might allow liquid water and just maybe life. Kepler 452b, dubbed Earth's cousin, orbits a Sun-like star every 385 days, while Proxima Centauri b, just 4 light-years away, basks in the faint glow of our nearest stellar neighbor. The implications are staggering. If life can take hold in Earth's relatively mild conditions, what might thrive on a super-Earth with double our gravity, or a tidally locked world where one side bakes in eternal daylight while the other freezes in endless night? Then there are the cosmic misfits planets that shouldn't exist at all. Pulsar planets, like those orbiting the corpse of a dead star in the Virgo constellation, endure relentless blasts of radiation that should have vaporized them billions of years ago. Rogue planets untethered from any star drift through the interstellar void, their surfaces frozen in perpetual darkness. Some may even harbor subsurface oceans, heated by radioactive decay or tidal forces, turning these nomads into potential oases for extremophile life. The most tantalizing discoveries lie in the atmospheres of these distant worlds. Spectroscopy, the art of decoding starlight filtered through an exoplanet's air, has detected water vapor, methane, even potential biosignatures like oxygen and phosphine. On K218b, a Hycean planet with a hydrogen-rich atmosphere and global oceans, conditions might be just right for aquatic life. But here's the catch: every signal is a puzzle. A molecule like methane could hint at biology, or it could be the byproduct of geologic activity we don't yet understand. What makes exoplanet science so exhilarating is its sheer unpredictability. For centuries, we assumed other solar systems would resemble ours. Instead, we found hot Jupiters orbiting closer to their stars than Mercury, or systems where planets circle twin suns like Tatooine from Star Wars. Every new telescope, from the James Webb Space Telescope to next-generation observatories like the Extremely Large Telescope, promises to peel back another layer of this cosmic onion. And with each revelation, we're forced to confront a humbling truth. The universe doesn't just exceed our imagination, it obliterates it. The hunt for exoplanets isn't just about cataloging strange new worlds. It's a quest to answer humanity's oldest question: are we alone? Whether we find microbial life in the clouds of Venus like exoplanets or detect the industrial pollution of a distant civilization, the discovery will redefine our place in the cosmos. Until then, every twinkle of starlight holds a secret, and every oddball planet, from diamond-studded giants to rogue wanderers, reminds us that the universe is far weirder and far more wonderful than we ever dared to dream. The cosmic microwave background is like a fossilized whisper from the universe's infancy, a faint glow that's been traveling for over 13 billion years, carrying secrets from the moment everything began. Picture the Big Bang not as an explosion in space, but as the sudden expansion of space itself, a fireball of energy so intense that it took hundreds of thousands of years just to cool enough for light to break free. That first light, now stretched into microwave wavelengths by the universe's expansion, is the CMB, a snapshot of the cosmos when it was just a newborn, barely 300,000 years old. What makes this ancient afterglow so revealing? Those subtle variations in temperature, tiny flickers no stronger than 100,000th of a degree are cosmic breadcrumbs. They mark the seeds of all structure in the universe, the gravitational tug-of-war spots where matter would eventually clump into galaxies and superclusters. Without these infinitesimal fluctuations, the cosmos would be a featureless void, stars and planets never forming. But here's where it gets weirder. The patterns in the CMB don't quite match our expectations. The fluctuations should be random, scattered like static on an old TV. Instead, some regions appear oddly aligned along what scientists jokingly call the axis of evil, a mysterious directional preference that, if real, suggests the universe might be fundamentally lopsided. Could this mean our entire cosmological model is missing a piece? One theory points to cosmic inflation, a hypothetical moment when the universe expanded faster than light in its first fraction of a second. Inflation would explain why the CMB is so uniform overall, but it also predicts symmetry. The axis of evil defies that, hinting at something stranger. Perhaps the universe is finite, shaped like a hall of mirrors, or influenced by a neighboring reality's gravity before inflation even began. Others propose that we're seeing the imprint of a pre-Big Bang era, a shadow of whatever came before space-time as we know it. Then there's the cold spot, a bizarrely frigid region in the CMB spanning nearly 1 billion light-years. Some speculate it's a bruise from a collision with another universe during inflation, evidence of a multiverse brushing against our own. Others argue it's just a statistical fluke, a cosmic mirage. But with each new experiment, like the European Space Agency's Planck satellite mapping the CMB in unprecedented detail, the anomalies only grow more puzzling. What's at stake isn't just a tweak to the textbooks. If the CMB's quirks are real, they could upend our understanding of gravity, dark energy, or even the nature of time. Imagine discovering that the universe has a preferred direction, like a tilted painting. How would that change our place in it? Or confirming that our cosmos is one bubble among many, each with different physical laws. The CMB isn't just a relic, it's a cipher waiting for the right key to unlock the universe's deepest mysteries. And every time we think we've cracked it, the cosmos throws us another curveball. White holes are the universe's great cosmic contradiction, theoretical yin to black holes' yang. While black holes are infamous for their relentless appetite, trapping even light in their gravitational grip, white holes would be their exact opposite, cosmic fountains, violently ejecting matter and energy with no way back in. Einstein's equations allow for their existence, but spotting one is another matter entirely. Imagine a black hole played in reverse, a singularity that refuses to swallow anything, instead spewing out particles and radiation like an unstoppable geyser. The mathematics is elegant, but the reality, that's where things get messy. One tantalizing possibility is that white holes could explain some of the most energetic explosions in the cosmos. Gamma-ray bursts, those blinding flashes of high-energy light that outshine entire galaxies for a few seconds, might be white holes briefly flickering into existence. Picture a dying black hole after billions of years of Hawking radiation, finally collapsing only to rebound as a white hole, releasing all its pent-up energy in a single catastrophic burst. It's a cosmic resurrection, turning the ultimate end into a fiery new beginning. But the wildest theories take it even further. Some physicists speculate that white holes could be the birth cries of entirely new universes. Inside a black hole's crushing singularity, space and time might collapse so violently that they bounce, spawning a fresh space-time bubble with its own laws of physics. Our entire universe could, in this scenario, be the white hole offspring of a long-dead black hole from another reality. It's a dizzying thought. Every black hole in our cosmos might secretly be a cosmic womb, nurturing infant universes we'll never see. The catch: white holes violate the second law of thermodynamics, which says entropy or disorder always increases. A white hole's orderly, one-way flow of energy defies this, making them statistically improbable. Unless, that is, they're not permanent structures but fleeting events, popping in and out of existence like quantum foam. Others argue they might be hidden behind event horizons just like black holes, making them indistinguishable from the outside until they erupt. What makes white holes so fascinating isn't just their defiance of physics as we know it, it's what they represent. If real, they'd be the universe's ultimate recyclers, turning destruction into creation, endings into beginnings. They hint at a cosmos far more dynamic and interconnected than we ever imagined, where even the most voracious monsters might one day become givers of light. Until we find proof, though, they remain one of astrophysics' most tantalizing what-ifs, a reminder that the universe's strangest possibilities are often hiding in plain sight. The Great Attractor is the universe's ultimate cosmic tug-of-war, an invisible force so powerful it's pulling entire galaxies, including our own Milky Way, toward it at nearly 2 million miles per hour. Picture a river of galaxies, thousands of them, all streaming in the same direction like leaves caught in a celestial current. At the center of this mystery lies something with the gravitational pull of 1 billion suns, an enigma so shrouded by the Milky Way's own dust and stars that we've never directly seen it. What could be bending the cosmos to its will? For decades, astronomers have pieced together clues from the strange motion of galaxies in our local universe. Even after accounting for the expansion of space, something was off. Galaxies weren't just drifting apart, they were being dragged sideways toward a point in the constellation Centaurus. The culprit, a gravitational anomaly so colossal it defies easy explanation. At first, scientists thought it might be the Norma cluster, a dense gathering of galaxies about 250 million light-years away. But the numbers didn't add up. The cluster's mass was significant, but nowhere near enough to account for the staggering pull. Then came the real twist. The Great Attractor might not be the final destination at all. Recent observations suggest our galactic river is flowing toward something even larger, the Shapley supercluster, a mind-bending assembly of galaxies over 600 million light-years away. This cosmic behemoth, one of the most massive structures in the observable universe, could be the true anchor behind the mystery, but here's where it gets stranger. Even Shapley's immense gravity might not fully explain the motion. Some theorists propose an unseen concentration of dark matter, a hidden scaffold of invisible mass warping spacetime on a scale we can't yet map. The most tantalizing possibility, the Great Attractor could be a glimpse into something far more profound, a flaw in our understanding of gravity itself. Modified Newtonian dynamics, or MUND, suggests that gravity behaves differently on cosmic scales, potentially eliminating the need for dark matter altogether. If true, the Great Attractor might not be a thing at all, but a signpost pointing to deeper laws of physics waiting to be uncovered. What makes this mystery so gripping isn't just the scale of the forces at play, but the humbling reminder of how much of the universe remains hidden in plain sight. Even with our most advanced telescopes, we're still peering through a keyhole, catching fragments of a reality far stranger than we've imagined. Every answer we find only peels back another layer, revealing just how little we truly know about the cosmic currents shaping our journey through the void. Fast radio bursts are the universe's most enigmatic Morse code, blinding flashes of energy that last less than the blink of an eye, yet pack more power than the sun emits in decades. Picture a cosmic strobe light flickering from billions of light-years away, so intense it briefly outshines entire galaxies. Most vanish as quickly as they appear, leaving astronomers scrambling to trace their origins. But a handful defy expectations, repeating in patterns so precise they've ignited whispers of something far stranger than natural astrophysics. The first fast radio burst, detected in 2007, was initially dismissed as a telescope glitch. Then came the repeating signal from a dwarf galaxy 3 billion light-years away, FRB 12-1102, pulsing like clockwork every 157 days. This wasn't random static, it had rhythm, a cadence that mirrored nothing seen in nature. Theories exploded, colliding neutron stars, eruptions from Magnetar's highly magnetic stellar corpses, or even the collapse of theoretical cosmic strings. But the more we studied, the weirder it got. Some bursts arrive with a polarized twist, their radio waves spiraling like a corkscrew, a fingerprint of extreme magnetic environments or perhaps engineered signals. Then there's the sheer energy. A single millisecond burst can release as much power as 500 million suns. Natural explanations struggle to account for such focused, fleeting violence. Magnetars, the leading suspects, occasionally produce similar flares, but none match the most distant bursts' intensity. Could these be the dying screams of stars being shredded by black holes? Or echoes of exotic physics, like action stars, hypothetical clumps of dark matter evaporating in a blink? But the elephant in the room remains: what if some aren't natural at all? The repeating patterns have fueled speculation about artificial origins, from alien megastructures harnessing star power to interstellar beacons deliberately sweeping the cosmos. Even the polarization could hint at engineered transmission, a way to encode information across galaxies. SETI scientists have scanned bursts for signs of modulation, embedded data, but so far silence. Still, the possibility lingers like static in the background of every discovery. What makes these bursts so thrilling isn't just their mystery, but their potential as cosmic tools. Their journey across the universe leaves subtle imprints, like fingerprints on glass. By measuring how their signals disperse, astronomers have mapped the missing matter between galaxies, the diffuse gas that makes up half the universe's atoms but had eluded detection. Each burst is a flashlight beam illuminating the dark corners of the cosmos, revealing structures we'd never see otherwise. Yet for every answer, new questions emerge. Why do some repeat while others vanish forever? What creates their staggering energy without leaving a visible trace? And could the most peculiar patterns be more than just celestial chaos? Until we catch one in the act, pinpointing its source, these fleeting whispers from the void will keep us balancing on the edge of revelation and wonder, reminding us that even in the quietest corners of space, the universe is shouting secrets we're only beginning to hear. The idea that our three-dimensional reality might be nothing more than an elaborate illusion, a holographic projection from a two-dimensional surface at the edge of the universe, sounds like the plot of a sci-fi thriller. Yet this isn't fantasy, it's a serious theory gaining traction among physicists. Imagine the entire cosmos as a movie screen, with every star, planet, and even your own body just a flickering image cast from information encoded on a distant, flat boundary. At first glance, it seems absurd. How could the richness of our world, the depth of a canyon, the swirl of a galaxy be reduced to data on a two-dimensional surface? But the math doesn't lie, and the implications are staggering. This radical notion, known as the holographic principle, emerged from an unexpected place: the study of black holes. When scientists calculated how much information a black hole could contain, they hit a paradox. The entropy, or disorder, of a black hole seemed to scale with its surface area, not its volume. In other words, all the data needed to describe what's inside a black hole could fit perfectly on its event horizon, like a cosmic hard drive. Extend that idea to the entire universe, and you've got the holographic principle. Every particle, every force, every moment in time might just be pixels in a grand cosmic projection. But how could this possibly work? Think of a credit card hologram, those shimmering images that seem to shift as you tilt them. The flat surface contains all the information needed to create a three-dimensional illusion. In the same way, the universe's boundary, if it even has one, could hold the blueprint for everything within it. Every interaction, every collision of atoms, every thought in your brain might be written in code on this distant surface, playing out in real time like a cosmic simulation. It's a dizzying thought. The solidity of your hands, the vastness of space, all might be shadows dancing on the walls of reality. What makes this more than just abstract philosophy are the tangible clues. Some versions of string theory, our leading framework for quantum gravity, naturally incorporate holography. In certain mathematical models, a higher dimensional universe can be perfectly described by physics operating on its lower dimensional boundary. It's as if the universe is a soup, and the holographic principle is the recipe written on the can's label, containing all the information needed to reconstruct it. Experiments with quantum entanglement even hint at this interconnectedness, with particles instantaneously influencing each other across vast distances, as if they are threads in a deeper, hidden fabric. The holographic principle doesn't just reshape our understanding of space, it redefines time itself. If the past, present, and future are all encoded on the universe's boundary, then time might not flow the way we experience it. Like frames in a movie, our perception of moments ticking by could be an emergent property, an illusion created by how the hologram is projected. This could solve some of physics' biggest headaches, like unifying quantum mechanics with general relativity, or explaining why the universe appears fine-tuned for life. Yet the most profound implication isn't about equations, it's about us. If reality is a hologram, then the line between observer and observed blurs. Your consciousness, your very sense of self, might be part of the projection, a fleeting pattern in the cosmic code. It's a humbling thought. We're not just living in the universe, we're expressions of it, temporary ripples in an infinite sea of information. Whether the holographic principle holds up to future tests or not, it's already achieved something remarkable. It's made the familiar strange again, reminding us that the universe is far weirder and far more wondrous than it appears. The universe as we know it hangs in a precarious balance held together by invisible fields that dictate the very rules of reality. Among them, the Higgs field is perhaps the most crucial, an unseen ocean of energy that gives particles their mass. Without it, atoms would fly apart, stars would never ignite, and life as we know it couldn't exist. But what if this field isn't as stable as we think? Lurking in the equations of quantum physics is a chilling possibility. The Higgs field might not be in its lowest energy state. Instead, it could be trapped in a false vacuum, like a marble resting on a ledge, seemingly stable, but one nudge away from plummeting into a deeper, more stable valley. If that nudge ever comes, the consequences would be unimaginable. A tiny patch of space could suddenly drop to this lower energy state, forming a bubble of true vacuum, where the laws of physics as we know them no longer apply. This bubble would expand at the speed of light, its walls rewriting reality itself. Atoms would disintegrate, forces would unravel, and every structure in the universe, planets, stars, galaxies, would vanish in an instant, replaced by a new cosmic order with rules we can't even predict. The scariest part, we wouldn't see it coming. One moment, everything would be normal. The next, an unstoppable wave of annihilation would erase existence before any signal could reach us. The odds of this happening are astronomically low. The Higgs field has likely remained stable for nearly 14 billion years, and the energy barrier keeping it in place is enormous. But the possibility isn't zero. Some theories suggest that high-energy particle collisions, like those in the Large Hadron Collider, could in theory create the conditions for vacuum decay. Thankfully, calculations show the energy required is far beyond what we can produce. Even cosmic events like magnetar flares or colliding neutron stars probably don't pack enough punch. But the universe is vast and ancient, and over infinite time, even the unlikeliest events become inevitable. What makes vacuum decay so haunting isn't just its destructive potential, it's what it reveals about the universe's fragility. The constants we rely on, the laws we take for granted, might not be permanent. They could be local quirks, temporary conditions in a much larger, stranger multiverse where physics plays by different rules. Even if vacuum decay never occurs, its very possibility humbles us, a reminder that the cosmos is far more dynamic and far more mysterious than it appears. In the grand scheme of things, we're living on borrowed time in a universe that could, at any moment, decide to rewrite its own rules. In October 2017, astronomers spotted something that shouldn't have been there, a strange, elongated object hurtling through our solar system at breakneck speed. Named Oumuamua, Hawaiian for scout or messenger, it was the first confirmed visitor from another star system, but this wasn't just any space rock. Its bizarre shape, a cigar-like structure nearly 10 times longer than it was wide, defied all expectations. Most asteroids and comets are lumpy and irregular, yet Oumuamua looked like it had been sculpted by some unseen hand. Then came the real shock. As it raced away from the sun, it accelerated faster than gravity alone could explain. At first, scientists assumed outgassing, the venting of gases from a comet's icy surface, was the culprit. But Oumuamua showed no visible tail, no cloud of dust or vapor. Next came the hydrogen iceberg theory. Perhaps it was a chunk of frozen hydrogen, evaporating invisibly in sunlight. But hydrogen ice is so fragile, it's unclear how such an object could survive the heat of interstellar space. The more we studied it, the stranger it became. Its brightness flickered erratically, as if tumbling end over end, and its surface was unusually reflective, almost metallic. Then came the most controversial idea: could Oumuamua be artificial? Harvard astronomer Avi Loeb famously suggested it might be a light sail, an alien probe propelled by starlight. The object's thin, flat profile and unexplained acceleration fit the profile of a technology harnessing radiation pressure. Skeptics dismissed the notion, pointing out natural explanations, however exotic, are always more likely, but Oumuamua's true nature remains unresolved. By the time we spotted it, it was already speeding away, leaving behind a trail of unanswered questions. What makes Oumuamua so fascinating isn't just its mystery, but what it represents. For centuries, we've assumed interstellar visitors would resemble the comets and asteroids we know. Oumuamua shattered that assumption, proving the universe is far more inventive than our models predict. If objects like this drift between stars routinely, how many have we missed? And what other cosmic oddities might be lurking in the dark, waiting to upend our understanding of the cosmos? The next time an interstellar traveler passes through, we'll be ready. Telescopes like the Vera C. Rubin Observatory, set to scan the entire sky every few nights, promise to catch these fleeting visitors sooner. Perhaps then we'll finally unravel Oumuamua's secrets or stumble upon something even stranger. Until then, it stands as a tantalizing reminder. The universe is full of surprises, and we've only just begun to explore. Einstein's theory of relativity paints the cosmos in sweeping strokes: planets orbiting stars, galaxies warping spacetime, black holes bending light into impossible curves. Meanwhile, quantum mechanics zooms in on the subatomic realm, where particles flicker in and out of existence and entanglement defies distance. Both theories work flawlessly in their own domains, but when they collide, the universe's rulebook tears apart at the seams. Black holes epitomize this cosmic standoff. Relativity says their immense gravity traps everything, even light, while quantum mechanics insists information can never truly vanish. The result, a paradox so profound it hints at something deeper: the need for a theory of quantum gravity, a framework to marry these two warring visions of reality. String theory offers one compelling solution: Imagine the universe's fundamental building blocks aren't point-like particles but vibrating strings, each note in their microscopic symphony corresponding to a different particle or force. In this elegant vision, gravity emerges naturally from the dance of these strings, bridging the gap between the quantum and cosmic scales. But there's a catch. String theory requires extra dimensions, 6 or 7 more than we perceive, curled up so tightly they're invisible. While the math is beautiful, experimental proof remains elusive, leaving some to wonder if we're chasing a mathematical mirage. Loop quantum gravity takes a starkly different approach. Instead of strings, it proposes space-time itself is woven from tiny, indivisible loops, a fabric of interwoven threads where gravity arises from their knots and twists. Here, black holes aren't bottomless pits but dense tangles of space-time, and the Big Bang wasn't a singularity but a bounce from a previous universe's collapse. It's a radical reimagining of cosmic origins, one that banishes infinity from physics equations. Yet like string theory, it's a framework in search of evidence, a blueprint without a construction site. The stakes couldn't be higher. Without quantum gravity, the universe's most pivotal moments, like the Big Bang's first incomprehensible flicker, remain shrouded in mystery. Was it truly a singularity, or did quantum effects smooth it into something finite? And what happens inside a black hole's heart? Does space-time dissolve into foam, or does it gateway to another realm? These aren't just academic puzzles. The answers could redefine causality, rewrite the lifespan of the cosmos, or even reveal hidden layers of reality. For now, we're left with clues scattered like breadcrumbs. Gravitational waves ripple from colliding black holes, carrying hints of how space-time behaves under extreme strain. Particle accelerators push energies closer to the conditions of the early universe, probing where quantum and gravitational forces might intersect. Even the humble photon, racing across billions of light-years, might bear subtle imprints of quantum gravity's fingerprints if we learn how to look. The quest for quantum gravity isn't just about equations. It's about reconciling two seemingly irreconcilable visions of reality. Whether through strings, loops, or some yet undiscovered third path, the solution will force us to rethink everything from the fabric of spacetime to the nature of existence itself. Until then, the universe keeps its deepest secrets guarded, dangling them just beyond our reach like stars in a sky we're only beginning to map. Galactic cannibalism sounds like the plot of a cosmic horror story, but it's the universe's way of building the galaxies we know today. Picture the Milky Way not as a static island of stars, but as a voracious predator, slowly devouring smaller galaxies over billions of years. The evidence is written in the stars, streams of ancient stellar debris, like the Sagittarius dwarf galaxy, stretched into ribbons by our galaxy's gravity. These galactic leftovers are the crumbs of a long-term feast, revealing how the Milky Way grew into the spiral giant we call home. But the real spectacle is yet to come. In roughly 4 billion years, the Milky Way will collide with its closest neighbor, the Andromeda Galaxy. Imagine two colossal pinwheels of stars, each hundreds of thousands of light years across, spiraling toward each other in a slow-motion dance. The gravitational forces will warp their shapes, flinging stars into chaotic new orbits and igniting bursts of star formation as gas clouds collide. The night sky for any future observers, human or otherwise, will transform into a dazzling fireworks display, with Andromeda swelling from a faint smudge into a brilliant disk before merging completely. Yet, despite the cosmic chaos, Earth and our solar system will likely emerge unharmed. Stars are so far apart that even during a galactic collision, the chances of two colliding are vanishingly small. It's like throwing two handfuls of sand into the air. Most grains will pass right by each other. The real threat isn't stellar smash-ups but the gravitational turmoil that could nudge our solar system into a new orbit, farther from the galaxy's core or even hurled into the intergalactic void. These mergers aren't just destruction, they're rebirth. Every galaxy we see today, from majestic spirals to glowing ellipticals, was forged through countless collisions. The Milky Way's past meals left behind globular clusters, those dense balls of ancient stars orbiting its halo. And when Andromeda finally merges with us, the result will be a new hybrid galaxy, nicknamed Milkdromeda, a vast elliptical blob where the two once distinct spirals become one. What makes galactic cannibalism so fascinating isn't just the scale of the violence, but the way it shapes the universe's story. Without these mergers, galaxies would remain small and isolated, lacking the raw material to birth new stars. The atoms in your body, the iron in your blood, were forged in generations of stars that only existed because of these cosmic collisions. We're the products of a universe that builds through chaos, where destruction and creation are two sides of the same coin. And in 4 billion years, the Milky Way's final act, a fiery tango with Andromeda, will write the next chapter in that epic saga. Neutrinos are the universe's most elusive ghost particles, so ethereal they slip through planets like moonlight through a window. Every second, trillions of them stream through your body, leaving no trace, as if you were nothing more than a whisper in their path. Born in the nuclear furnaces of stars, the violent deaths of supernova, and even the radioactive decay deep inside Earth, these phantoms carry secrets from the cosmos' most extreme environments. Yet, for all their abundance, catching a neutrino in the act is like trying to grab a shadow. Most will travel through light years of lead without a single interaction, their presence detectable only by the rarest flicker of evidence in sprawling underground detectors. What makes these particles so fascinating isn't just their stealth, it's the puzzle they pose to physics. Neutrinos were long thought to be massless, moving at the speed of light like their photon cousins. Then came the bombshell: they oscillate. A neutrino born in the sun might transform into a different flavor by the time it reaches Earth, a magic trick only possible if it has some tiny amount of mass. This discovery upended the standard model of particle physics, forcing scientists to ask, why do neutrinos weigh anything at all? The answer could lie in entirely new physics, perhaps particles we've yet to discover or hidden symmetries in the fabric of reality. But the implications run even deeper. Neutrinos might hold the key to one of the universe's greatest mysteries. Why does anything exist at all? In the Big Bang's aftermath, matter and antimatter should have annihilated each other perfectly, leaving behind a lifeless void. Instead, a tiny excess of matter survived just one particle in a billion, and here we are. Neutrinos, with their subtle preference for matter over antimatter in certain interactions, could be the smoking gun. If their oscillations violate a fundamental symmetry called CP violation more strongly than we've seen, they might explain how the universe tipped the scales in favor of stars, planets, and us. Detecting these ghostly messengers requires feats of engineering as extreme as the particles themselves. Take Japan's Super Kamiok and a tank buried deep underground, filled with 50,000 tons of ultra-pure water, lined with sensors waiting for the faint blue glow of a neutrino collision. Or IceCube, a telescope carved into Antarctic ice, hunting for neutrinos that scream through space at energies dwarfing anything our particle accelerators can produce. These experiments aren't just chasing shadows, they're decoding messages from the hearts of collapsing stars and the fiery cores of distant galaxies. The most tantalizing neutrinos of all might be the relic ones, left over from the Big Bang itself. Older than the cosmic microwave background, These ancient particles could map the universe's infancy in ways light never can. If we ever learn to read their faint signals, they'd be a time machine, revealing moments just a fraction of a second after creation. Neutrinos remind us that the universe's most profound truths often hide in plain sight, or rather, pass through it unnoticed. They're cosmic scribbles in a language we're still learning, whispering hints about everything from the sun's core to why the cosmos didn't vanish before it began. And with every flicker of detection, we're one step closer to deciphering their ghostly code. The black hole information paradox is one of the most vexing puzzles in modern physics, a cosmic tug of war between two pillars of science that refuse to play nice. On one side, quantum mechanics insists that information, the fundamental blueprint of reality, can never be destroyed. Flip a coin, burn a book, or vaporize a hard drive. The underlying information might scatter, but it never disappears entirely. On the other side, black holes defy this rule with terrifying efficiency. When matter crosses the event horizon, it's crushed into oblivion, leaving behind only mass, charge, and spin. Three simple numbers that erase a universe of detail. And when the black hole eventually evaporates via Hawking radiation, what happens to all that swallowed information? Does it vanish forever, or is it somehow preserved in a way we can't yet see? This paradox isn't just academic, it strikes at the heart of reality itself. If black holes truly erase information, then causality, the unbreakable chain linking cause and effect, frays at the edges. The past becomes unknowable and the future unpredictable. To resolve this, physicists have proposed solutions so radical they sound like science fiction. Take the holographic principle, which suggests that all the information swallowed by a black hole isn't lost inside, but is instead smeared across its event horizon, like a cosmic fingerprint. Imagine a library burning down, but every book's contents are somehow encoded in the smoke rising from the flames. In this view, the three-dimensional chaos inside the black hole is projected from a two-dimensional surface, preserving information in a form we don't yet understand. Then there's the firewall hypothesis, a concept so unsettling it nearly redefines the nature of black holes. If information can't be destroyed, but also can't escape, maybe it piles up at the event horizon, creating a searing wall of energy that incinerates anything falling in. Forget the gentle stretch of spaghettification. Crossing the horizon would mean instant annihilation. This idea splits the difference between quantum mechanics and relativity, but at a cost. It turns the event horizon from a silent threshold into a cosmic shredder, violating Einstein's vision of smooth, continuous spacetime. The stakes couldn't be higher. Solving the paradox might require rewriting the laws of physics, merging quantum mechanics and gravity into a single, unified theory. Some researchers argue that black holes don't evaporate completely, but leave behind microscopic remnants, quantum fossils packed with compressed information. Others propose that information escapes via Hawking radiation, scrambled beyond recognition but technically preserved, like a shattered vase whose pieces could theoretically be reassembled. What makes this debate so electrifying isn't just the intellectual challenge, it's the glimpse it offers into the universe's deepest workings. Black holes aren't just cosmic vacuum cleaners, they're laboratories where the rules of reality are stress-tested to their limits. Whether the answer lies in holograms, firewalls, or something even stranger, one thing is certain: cracking the information paradox won't just explain black holes, it'll reveal the hidden language of the cosmos itself. Pulsars are the universe's ultimate timekeepers, cosmic metronomes ticking with such precision they make the finest atomic clocks seem sluggish. Born from the violent deaths of massive stars, these neutron stars spin at dizzying speeds, some rotating hundreds of times per second. their intense magnetic fields funneling beams of radiation into space like interstellar lighthouses. Every pulse, every flicker of light or radio wave arrives with clockwork regularity, a rhythm so steady it's used by astronomers to navigate the Milky Way and test Einstein's theory of relativity with unmatched precision. But what makes pulsars truly astonishing isn't just their reliability, it's their resilience. These stellar corpses pack more mass than the Sun into a sphere no wider than a city, creating gravitational forces so intense that a sugar cube's worth of their material would weigh as much as a mountain. Yet, against all odds, some pulsars host planets. Imagine a world orbiting one of these spinning powerhouses, bathed in relentless radiation, its skies lit not by gentle sunlight but by searing pulses of X-rays and gamma rays. The fact that such planets exist at all is a testament to the universe's ability to defy expectations, thriving even in the most hostile environments. Pulsars also serve as cosmic laboratories, pushing the boundaries of physics. When two pulsars orbit each other, their dance creates ripples in space-time gravitational waves that slowly sap their energy, causing them to spiral inward. By tracking these subtle changes, scientists have confirmed predictions of general relativity with pinpoint accuracy, proving that even in death, stars can illuminate the deepest truths of the cosmos. Then there's the mystery of the Black Widow pulsars, ultra-fast spinners that blast their companion stars with radiation, slowly evaporating them into oblivion. These cosmic predators are locked in a deadly embrace, their gravitational pull stripping material from their partners, while their beams of energy scorch away anything left behind. It's a brutal but mesmerizing spectacle, one that reveals how pulsars can reshape their surroundings long after their birth in supernova explosions. Beyond their destructive potential, pulsars are also galactic cartographers. Their beams cut through the Milky Way's magnetic fields, revealing the invisible forces that shape our galaxy. By measuring how these signals twist and polarize as they travel, astronomers map the vast, tangled web of magnetic lines that crisscross interstellar space, a hidden framework guiding everything from star formation to the paths of cosmic rays. Perhaps the most humbling thought is that pulsars are fleeting by cosmic standards. Over millions of years, their spins slow, their beams fade, and they vanish into the dark. But for now, they're among the universe's most brilliant tools, flashing their signals across the void, reminding us that even in death, stars continue to light the way. Cosmic strings sound like something ripped from the pages of a theoretical physicist's wildest daydream, infinitely long, impossibly thin threads of pure energy, thinner than an atom yet dense enough to bend the fabric of spacetime itself. Picture the universe in its earliest moments, a seething cauldron of energy cooling into the reality we know today. As temperatures dropped, cracks might have formed in the structure of spacetime like fissures in freezing ice. These defects, if they exist, would be cosmic strings, remnants of a time when the laws of physics were still setting into place, frozen relics from the birth of everything. What makes these hypothetical strings so mesmerizing isn't just their origin, it's what they could do. A single cosmic string, thinner than a proton but stretching across the entire universe, would carry unimaginable gravitational power. If one passed through our solar system, it wouldn't just tug on planets, it would slice through space like a wire through cheese, leaving behind a wake of distorted reality. Light bending around it would create double images of stars, a phenomenon called gravitational lensing, while time itself would stutter and warp in its presence. The math even suggests that if two strings crossed or a looped string collapsed, the resulting energy could be so extreme it might birth a black hole or twist spacetime into a closed time-like curve, a fancy term for a time machine. The wildest part, unlike black holes or neutron stars, cosmic strings wouldn't just warp space-time, they'd fracture it. Imagine drawing a circle around a string. Normally, the circumference of a circle is always 2 pi times its radius. But with a cosmic string threading through the center, the math changes. Complete the loop, and you'd find yourself just shy of a full 360 degrees, as if space itself had a wedge cut out of it. This angle deficit means parallel lines near a string wouldn't stay parallel, and objects passing by would experience reality in a way that defies everyday intuition. So why haven't we found one? Cosmic strings would be nearly invisible, emitting no light and only betraying their presence through subtle gravitational fingerprints. Astronomers have searched for their signatures in the cosmic microwave background, hunting for telltale distortions in the afterglow of the Big Bang. Others have scoured the skies for pairs of identical galaxies lined up just so, a potential mirage caused by a string's lensing effect. So far, no luck. But the hunt isn't over. If strings exist, they might vibrate like plucked guitar strings, sending ripples through space-time that next-generation gravitational wave detectors could catch. The implications of discovering a cosmic string would be staggering. It'd be like unearthing a fossil from the universe's first trillionth of a second, offering clues about how symmetry broke in those chaotic early moments. Were there multiple kinds of strings? Did they tangle into a primordial network, seeding the large-scale structure of galaxies we see today? And yes, could we ever harness their space-time warping properties for far-fetched feats like time travel? Theoretically, yes, but the engineering would make building a Dyson sphere look like child's play. For now, cosmic strings remain one of the most tantalizing what-ifs in cosmology. They're a reminder that the universe's infancy might have left behind scars we've yet to trace, scars that could rewrite our understanding of reality's deepest layers. Whether they're out there or not, the mere possibility stretches our imagination, proving once again that the cosmos is stranger than anything we could invent. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary, a burst of noise so powerful, so unexpected, that astronomer Jerry Rood circled it on the printout and scribbled, "Wow." In the margin, that single word would give the signal its name and its legend. For 72 seconds, the Big Ear telescope recorded a narrowband radio pulse 30 times louder than the background noise, perfectly aligned with the frequency hydrogen emits in space, a logical choice for any civilization trying to announce its presence. Then, just as suddenly as it began, it vanished. No replay, no echo, no trace. Decades of searching the same patch of sky have turned up nothing. The wow. Signal's mystery lies in its perfection. Natural cosmic static tends to be messy, smeared across frequencies. This was surgically precise, like a laser beam cutting through cosmic noise. It came from the direction of the constellation Sagittarius, where no known stars or planets could explain it. Comets, none were in the area at the time. Satellite interference, no human-made object matched the signal's profile. Even today, with telescopes far more sensitive than Big Ear, we've caught nothing like it, a cosmic flare that burned bright once and never again. Then there's the chilling possibility that it wasn't natural. The hydrogen line frequency isn't just scientifically significant. It's a universal landmark, a logical hailing channel any advanced civilization might use. If aliens were behind the wow signal, why hasn't it repeated? One theory suggests it could have been a fleeting beacon, a lighthouse sweep from a distant star that our telescope happened to catch mid-pulse. Or perhaps it was targeted, a deliberate, one-time message meant for someone else, and Earth just happened to drift into the crossfire. The most haunting question isn't about aliens, though, it's about us. The WOW signal arrived at a time when humanity was just learning to listen beyond our atmosphere. Since then, we've built vast arrays like the Allen Telescope Array, scanning thousands of frequencies simultaneously. Yet silence persists. Was the WOW signal a cosmic prank, a fluke we'll never understand? Or is it proof that the universe teases us with glimpses of something greater, just beyond our reach? Until another signal comes, if it ever does, those 72 seconds remain frozen in time, a whisper from the void we're still straining to hear. The Kuiper Belt is more than just a distant junkyard of frozen leftovers. It's a time capsule preserving the solar system's rawest, most untouched ingredients. Stretching beyond Neptune's orbit, this shadowy realm is home to Pluto, Haumea, Makemake, and countless other icy bodies, each whispering secrets about how our cosmic neighborhood came to be. But the deeper we look, the stranger the story gets. Take Arrokoth, the most distant object ever visited by a spacecraft. When New Horizons zipped past it in 2019, it revealed a bizarre, snowman-shaped world, untouched by collisions or heat for over 4 billion years. This primordial relic isn't just a pair of glued-together ice chunks, it's a fossil from the dawn of the solar system, showing how tiny particles gently clumped into the building blocks of planets. Yet Arrokoth's serene existence is the exception, not the rule. The Kuiper Belt is also a stage for cosmic chaos, where entire populations of objects dance to the tune of an invisible conductor. Some, like Sedna and a handful of other extreme trans-Neptunian objects, follow wildly elongated orbits that defy easy explanation. They swing so far from the sun that traditional models of solar system dynamics can't account for them. The leading theory, a hidden giant dubbed Planet 9 lurking in the darkness, its gravitational pull shepherding these misfits into their strange paths. This hypothetical world, estimated to be 5 to 10 times Earth's mass, could be the solar system's last undiscovered planet, but finding it is like searching for a black cat in a coal cellar. Its orbit, if it exists, would take 10 to 20,000 years to complete, and its faint glow would be drowned out by the Milky Way's stellar backdrop. The Kuiper Belt's mysteries don't stop there. Some objects, like Pluto's moon Charon, hint at violent past collisions so colossal they reshaped entire worlds. Others, like the blue-tinged Haumea, spin so fast they've been stretched into ellipsoids, their surfaces scarred by ancient impacts. And then there's the Great Kuiper Belt Cliff, a sudden drop-off in objects beyond a certain distance, as if someone drew a cosmic boundary line. Is this the edge of the solar system's original construction zone, or did a passing star steal our outer debris billions of years ago? Every probe we send, every telescope we point toward this icy frontier peels back another layer of the puzzle. The Kuiper Belt isn't just a relic of the past, it's a dynamic, evolving puzzle box daring us to crack its codes. Whether it's the ghostly tug of Planet 9, the pristine silence of Arrokoth, or the chaotic orbits of Sedna and its kin, one thing is clear: our solar system's story is far from finished. And the next chapter is waiting, frozen in the dark. Gamma-ray bursts are the universe's ultimate fireworks, cataclysmic eruptions of energy so intense they can briefly outshine every star in their host galaxy combined. Picture a single event releasing more power in 10 seconds than our Sun will emit across its entire 10 billion-year lifespan. These aren't just distant curiosities. They're cosmic alarms screaming from the edge of space-time, carrying messages about the most violent transformations matter can undergo. Most originate in two scenarios: the collapse of massive stars into black holes, where dying behemoths convulse in their final moments, or the mergers of neutron stars, those ultra-dense stellar corpses that create gravitational waves and forge gold in their wake. When a massive star exhausts its fuel, its core collapses under its own weight in seconds. As it implodes, twin jets of plasma hotter than a supernova blast outward at nearly light speed, punching through the star's outer layers like a cosmic blowtorch. These jets, focused into beams narrower than a laser pointer but spanning light years, become the gamma-ray burst we observe, a death scream transformed into the universe's most powerful lighthouse. Meanwhile, neutron star mergers take violence to another level. When two of these city-sized, hyper-dense objects spiral together, their collision doesn't just create gravitational ripples, it launches a similar jet of destruction, supercharged by the unfathomable magnetic fields at play. Earth isn't immune to their reach. A gamma-ray burst within a few thousand light-years, unlikely but possible, would bombard our atmosphere with enough high-energy radiation to chemically dismantle the ozone layer within weeks. The sudden UV exposure would trigger a cascade of ecological collapse, mirroring past mass extinctions but unfolding at breakneck speed. Historical events like the Ordovician extinction 450 million years ago, which wiped out 85% of marine species, have even been speculatively linked to a nearby burst. Thankfully, the Milky Way's structure and stellar demographics make such a catastrophe extraordinarily rare but not impossible. What makes these explosions invaluable isn't their destructive potential, but their role as cosmic laboratories. The jet's extreme conditions trillions of degrees, magnetic fields a quadrillion times Earth's, particles accelerated to velocities physics can barely describe offer glimpses into regimes no experiment on Earth could replicate. Some bursts even challenge our understanding of light speed, exhibiting phenomena where radiation appears to move faster than photons should through turbulent plasma. Others serve as mile markers for the early universe. The most distant known burst, detected in 2022, erupted when the cosmos was barely 2% of its current age, its light stretched by cosmic expansion into the infrared. Yet for all we've learned, mysteries linger. Why do some collapsing stars produce bursts while others fade quietly? What determines whether a burst lasts milliseconds or minutes? And could there be even more exotic sources, like primordial black holes or cosmic strings snapping? Every new detection peels back another layer, revealing how much we still don't understand about the universe's most extreme energy factories. These flashes in the dark aren't just explosions. They're telegrams from the edge of physics, written in radiation and decoded by the lucky observers who happen to be looking in the right place at the right cosmic moment. The Big Bang should have been the ultimate cosmic tie, a perfect balance between matter and antimatter, particles and their mirror opposites, colliding and annihilating in a flash of pure energy. Yet against all odds, matter won. For every billion particles of antimatter created in those first explosive moments, one solitary particle of matter survived. That razor-thin margin is the only reason stars, planets, or even you exist. But how? Why did the universe tip the scales so dramatically in favor of matter? This enigma, known as Baryon asymmetry, is one of physics' most profound puzzles, and the answer might lie in the tiniest cracks between the laws we think we understand. At CERN, scientists are recreating the conditions of the early universe, smashing particles together at nearly light speed to glimpse how matter and antimatter behave. The key lies in something called CP violation, a subtle cosmic favoritism where particles and their antiparticles don't quite mirror each other. Imagine flipping a coin and finding it lands on heads 51% of the time instead of 50. Over billions of flips, that 1% stacks up. In the same way, if certain particles decayed even slightly more often into matter than antimatter, it could explain our existence. So far, the evidence is maddeningly faint. Quarks, the building blocks of protons and neutrons, show a minuscule bias but not enough to account for the universe's overwhelming matter dominance. Neutrinos, those ghostly particles that barely interact with anything, might hold the missing piece. If they violate CP symmetry more dramatically than quarks, their fleeting interactions in the early universe could have seeded the imbalance we see today. Experiments like Japan's T2K and the upcoming Deep Underground Neutrino experiment are racing to catch these particles in the act, hoping to catch them breaking the rules just enough to explain why we're here. But what if the answer isn't in particles at all? Some theories suggest the imbalance came from something far more exotic: cosmic phase transitions in the infant universe, where space-time itself shifted like freezing water cracking into ice. These cracks could have released energy that preferentially produced matter, like a cosmic scale factory with a broken assembly line. Others propose that antimatter didn't vanish. It's hiding in vast, invisible regions of the cosmos, separated from us by domains of repulsive force we've yet to detect. The stakes couldn't be higher. If we solve Baryon asymmetry, we're not just explaining why atoms exist, we're peering into the universe's first moments, uncovering the flaws in symmetry that made life possible. Every star, every planet, every breath you take hangs on that fragile one in a billion imbalance. And until we crack it, the haunting question remains: are we the rule or the luckiest exception in the cosmos? Gravitational waves are the universe's silent symphony, ripples in the very fabric of spacetime, carrying whispers of collisions so violent they shake the cosmos itself. Einstein predicted their existence over a century ago, but it wasn't until 2015 that humanity finally heard them. The source: two black holes, each 30 times the mass of our sun, spiraling toward each other in a death spiral a billion light years away. When they merged, they unleashed a burst of energy so immense it briefly outshone every star in the observable universe combined. Yet all that reached Earth was an almost imperceptible tremor, a distortion smaller than the width of an atomic nucleus, caught by the Laser Interferometer Gravitational Wave Observatory, or LIGO. What makes this discovery revolutionary isn't just the confirmation of Einstein's theory. It's the birth of an entirely new way to observe the universe. Traditional astronomy relies on light, from radio waves to gamma rays, but gravitational waves let us hear the cosmos. It's like stepping into a pitch-black room and suddenly realizing you can sense the movement of objects by the vibrations in the air. LIGO and its European counterpart, Virgo, have since tuned into dozens of these cosmic events. Neutron stars crashing together, black holes devouring one another, even mysterious mergers where one object is too heavy to be a neutron star but too light to be a black hole. Each detection peels back another layer of the universe's hidden drama. The most tantalizing possibility lies ahead. Future observatories like the space-based LISA mission will cast a net across millions of kilometers, sensitive enough to catch gravitational waves from the dawn of time. These primordial ripples, born in the first chaotic moments after the Big Bang, could carry clues about how spacetime itself emerged. Did inflation, the universe's rapid expansion, leave a gravitational fingerprint? Are there echoes of cosmic strings or other exotic relics vibrating through the void? The answers might rewrite our understanding of reality's origins. But gravitational waves aren't just about the distant past. They're reshaping our present-day cosmic maps. When LIGO detected a neutron star collision in 2017, telescopes around the world swiveled to the same patch of sky, capturing the aftermath in every wavelength imaginable. The result, a goldmine of data confirming that these collisions forge heavy elements like gold and platinum, solving a long-standing mystery about the universe's chemical makeup. It's a reminder that spacetime's ripples aren't just abstract curiosities, they're threads connecting the grandest cosmic events to the atoms in our jewelry and electronics. The more we listen, the stranger the soundtrack becomes. Some black hole mergers spin wildly off kilter, hinting at chaotic origins. Others seem too massive to exist under current theories, challenging our models of stellar evolution. And then there are the mass gap objects, neither black hole nor neutron star, but something in between, defying classification. Each detection is a puzzle piece, forcing us to redraw the boundaries of what we thought possible. This is just the beginning. As detectors grow more sensitive, they'll uncover fainter, more distant events, perhaps even the faint hum of a universe teeming with gravitational waves, a background hiss from all the collisions we can't yet resolve. One day, we might even hear the echoes of microscopic black holes evaporating, or the vibrations of higher dimensions curled up in ways we can't yet imagine. Gravitational wave astronomy isn't just a new tool, it's a new sense, letting us perceive a universe that's been shouting all along, waiting for us to finally listen. Titan isn't just another frozen moon. It's a world with weather systems, shorelines, and even rain, but none of it involves water. Instead, Saturn's largest moon is drenched in liquid methane and ethane, forming rivers that carve valleys and vast seas larger than North America's Great Lakes. Picture standing on Titan's frigid surface, where temperatures plunge to negative 290 degrees Fahrenheit. The sky is a hazy orange, thick with nitrogen and organic compounds, and beneath your feet, the ground isn't rock but water ice as hard as granite. Overhead, methane clouds drift lazily before bursting into storms, sending droplets of liquid hydrocarbon splashing into alien lakes below. It's a landscape both eerily familiar and utterly alien, like Earth reflected in a funhouse mirror. What makes Titan so fascinating isn't just its bizarre hydrology, it's the tantalizing possibility that life could thrive there, just not as we know it. On Earth, water is the solvent that fuels biochemistry, but on Titan, methane takes its place. Imagine organisms with cell membranes not made of lipids but of flexible, nitrogen-rich molecules, floating in methane lakes or burrowing into icy crusts. These hypothetical life forms would breathe hydrogen instead of oxygen, metabolizing acetylene or ethane for energy. It sounds like science fiction, but lab experiments have shown that under Titan-like conditions, simple organic molecules can form complex structures eerily reminiscent of primitive cells. Parallels to early Earth are uncanny. Billions of years ago, before oxygen filled our atmosphere, our planet might have resembled Titan, a smoggy world rich in organic chemistry, ripe for the spark of life. Titan's thick atmosphere, loaded with compounds like cyanide and benzene, is a cosmic petri dish for probiotic reactions. Some scientists even speculate that beneath its icy shell, a subsurface ocean of liquid water could exist, heated by tidal forces from Saturn's gravity. If true, Titan could host two entirely separate environments where life might arise, one in the methane lakes above, and another in the hidden ocean below. NASA's Dragonfly mission, set to launch in 2027, aims to untangle these mysteries. This nuclear-powered drone, equipped with rotors to navigate Titan's dense atmosphere, will hop across the moon's surface like a robotic insect, sampling organic molecules and scouting for chemical signatures that hint at biological activity. It'll explore Shangri-La, a vast dune field near Selk Crater, where ancient organic material may have mixed with liquid water during impacts. Dragonfly won't just search for life, it'll test whether the building blocks of biology can assemble in the absence of water, rewriting our definition of habitability. Yet Titan's greatest surprise might be its sheer dynamism. Unlike most icy moons, its surface is geologically young, reshaped by cryovolcanoes spewing slushy ice and methane. Seasonal changes trigger massive storms, and some lakes appear to vanish and reappear over decades, suggesting hidden underground reservoirs. This isn't a static, frozen relic. It's a world with its own rhythms, its own cycles of erosion and renewal. The implications stretch far beyond Titan. If life can flourish in its methane seas, then the universe might be teeming with organisms in environments we've barely considered. Gas giants, moons, rogue planets drifting between stars, even exoplanets with hydrocarbon atmospheres, all could harbor their own versions of biology, evolved under rules we're only beginning to imagine. Titan isn't just a destination for exploration. It's a mirror held up to our assumptions, challenging us to think broader, to imagine stranger, and to wonder just how adaptable life truly is. The Sun's surface blazes at a staggering 10,000 degrees Fahrenheit, a temperature so intense it vaporizes metal instantly. Yet, just above this inferno, the corona, the Sun's wispy outer atmosphere, soars to millions of degrees, defying every law of thermodynamics we know. It's like walking away from a bonfire and suddenly feeling the air around you grow hotter instead of cooler. This cosmic contradiction, known as the coronal heating problem, has puzzled scientists for decades. How does the Sun's atmosphere become hundreds of times hotter than the surface beneath it? One leading theory points to the Sun's tangled magnetic fields. Imagine the Sun not as a smooth ball of fire, but as a seething cauldron of magnetism, with lines of force twisting, snapping, and reconnecting like invisible rubber bands. When these fields realign, they release explosive bursts of energy, nanoflares tiny compared to solar flares but trillions of times more frequent. Each one acts like a miniature bomb, heating the corona piece by piece. Another idea involves magnetic waves rippling outward from the Sun's churning interior, dumping energy into the corona like ocean waves crashing onto a shore. But even with satellites like NASA's Parker Solar Probe diving closer to the Sun than any spacecraft before, we still can't pinpoint the exact recipe for this cosmic oven. While the corona's heat is a mystery, its fury is undeniable. Solar flares, sudden flashes of X-rays and ultraviolet light erupt without warning, sometimes with the energy of 1 billion hydrogen bombs. Even more destructive are coronal mass ejections, billion-ton clouds of magnetized plasma hurled into space at millions of miles per hour. When one of these storms hits Earth, the results can be catastrophic. In 1859, the Carrington event, the most powerful solar storm on record, set telegraph wires ablaze and painted the skies with auroras as far south as Cuba. Today, a storm of that magnitude could fry satellites, knock out power grids for months, and plunge the modern world into a technological dark age. The problem isn't just the Sun's power, it's our inability to predict its outbursts. Unlike hurricanes or earthquakes, solar storms offer few reliable precursors. Current models can give us about 48 hours of warning, but with a frustratingly high margin of error. That's why missions like the European Space Agency's Solar Orbiter are racing to map the Sun's poles, where magnetic activity is thought to originate. By studying the Sun's global magnetic dance, scientists hope to uncover patterns that could turn solar forecasting into a life-saving science. What makes these solar mysteries so urgent isn't just their scientific intrigue, it's their real-world stakes. Our civilization now orbits in the crosshairs of the Sun's temper, reliant on delicate electronics vulnerable to its tantrums. A single well-aimed coronal mass ejection could disrupt GPS, cripple communications, and trigger blackouts costing trillions. Yet for all its danger, the Sun is also our greatest cosmic ally. Its light fuels life, its warmth stabilizes our climate, and its mysteries push us to unravel the fundamental physics of stars. Every breakthrough, whether it's decoding the corona's heat or predicting solar storms, brings us closer to coexisting safely with the fiery giant that both sustains and threatens us. The Sun isn't just a star, it's a reminder that understanding the cosmos isn't optional, it's survival. Beneath Mars' frozen polar caps, something extraordinary may be hiding, not in the barren, rust-colored deserts above, but deep underground, where radar signals have revealed tantalizing hints of liquid water. These aren't just puddles or damp soil, they're sprawling subsurface lakes, some spanning dozens of kilometers, buried under a kilometer of ice. The discovery sent shockwaves through the scientific community because where there's liquid water, there's the potential for life. But how can water remain liquid in a place where surface temperatures plummet to negative 150 degrees Fahrenheit? The answer lies in a cocktail of extreme chemistry and hidden geothermal forces. Dissolved salts like perchlorates could be acting as antifreeze, lowering the water's freezing point just as road salt melts ice on Earth. Alternatively, heat from Mars' interior, leftover from its volcanic past or produced by radioactive decay, might be warming these underground reservoirs, creating pockets of habitability beneath the ice. Imagine a Martian version of Antarctica's Lake Vostok, a liquid oasis sealed off from the surface for millions of years, possibly hosting microorganisms adapted to darkness and cold. If life exists there, it would be a game-changer, proving that biology can thrive in the most unforgiving corners of the cosmos. The implications stretch far beyond microbial hunts. These lakes could serve as natural resource depots for future human explorers, providing drinking water, oxygen, and even rocket fuel when split into hydrogen and oxygen. But accessing them won't be easy. Drilling through Martian ice demands technology that doesn't yet exist: robotic probes capable of penetrating thick, frozen barriers without contaminating the pristine environments below. NASA and ESA are already brainstorming missions like robotic ice moles or melt probes, inspired by devices used on Earth to explore subglacial lakes. Yet skepticism lingers. Some scientists argue the radar signals could be explained by layers of clay or other minerals, not liquid water. Others caution that even if the lakes are real, their extreme salinity or acidity might make them sterile. The only way to settle the debate: go there. Upcoming missions like NASA Mars Life Explorer could carry drills and sensors designed to sniff out organic molecules or even living cells. If they strike water and possibly life, it would rewrite our understanding of biology's limits, turning Mars from a dusty relic into a world teeming with hidden possibilities. What makes these hidden lakes so electrifying isn't just the science, it's the sheer audacity of the idea that Mars, a planet we've long written off as dead, might still hold secrets in its icy depths. Whether it's brine bubbling under pressure or geothermal vents creating oases in the dark, one thing is clear: the red planet isn't done surprising us. And if we're lucky, the next chapter in Martian exploration won't just be about rocks and dust, it'll be about diving into the shadows, chasing the ripples of something far more extraordinary. The Moon isn't the dead, unchanging world we once thought it was. Beneath its silent, cratered surface, our closest celestial neighbor is quietly shrinking, its crust wrinkling like the skin of a grape drying into a raisin. This slow contraction, driven by the Moon's cooling interior, creates thrust faults, cliffs that can tower dozens of meters high, snaking across the lunar landscape like scars. And when these faults slip, they trigger moonquakes, some strong enough to last for hours, far longer than their earthly counterparts. Apollo astronauts left seismometers behind in the 1970s, and the data they collected revealed a surprising truth. The moon is still geologically active, its surface creaking and groaning as it settles. What makes these moonquakes more than just a curiosity is their potential impact on future lunar exploration. Imagine setting up a permanent base near one of these faults, only to have the ground tremble violently, cracking habitats or disrupting delicate equipment. Some moonquakes reach magnitudes comparable to a 5 on the Richter scale, enough to cause serious damage if structures aren't built to withstand them. But there's a flip side to this seismic activity. The same forces that create these faults might also be shaping hidden underground networks of lava tubes, cavernous tunnels left behind by ancient volcanic flows. These natural passageways, shielded from the moon's harsh surface conditions, could be the perfect refuge for astronauts. Picture a lunar colony nestled inside one of these tubes, its walls acting as a natural barrier against deadly cosmic radiation, micrometeorite impacts, and extreme temperature swings. Sunlight could be channeled in through mirrors, while the stable underground environment, a constant -20 degrees Fahrenheit, would simplify climate control compared to the surface's wild swings between boiling day and freezing night. Scientists have already spotted potential skylights, collapsed sections of lava tubes that could serve as entrances to these subterranean havens. Missions like NASA's Artemis program aim to scout these locations, mapping the moon's underground labyrinths with ground-penetrating radar and robotic explorers. Yet the moon's shrinking surface isn't just a practical challenge, it's a window into its turbulent past. The same cooling process that's causing contraction today also shaped the moon billions of years ago, when its mantle was still molten and its crust thin and flexible. Studying these modern quakes helps us unravel how the moon formed, why its near and far sides look so different, and even how other small planetary bodies behave as they age. Every tremor is a clue, a whisper from a world we're only beginning to understand. The moon may be Earth's companion, but it's far from a mirror. Its geology, its rhythms, even its slow, silent collapse, all of it tells a story that's uniquely its own. And as we prepare to return, not just as visitors but as settlers, we're learning that the moon isn't just a destination. It's a dynamic world, one that demands respect, adaptation, and a willingness to listen to the quiet rumblings beneath our feet. Interstellar travel isn't just the stuff of science fiction anymore. It's a tangible goal, with projects like Breakthrough Starshot pushing the boundaries of what's possible. Imagine spacecraft no larger than a postage stamp, propelled by powerful lasers at a fifth the speed of light, racing toward Alpha Centauri in just 20 years. It sounds revolutionary, but the reality is far more complicated. Even at that blistering pace, these tiny probes would face a gauntlet of cosmic hazards, from microscopic dust grains hitting like bullets to relentless radiation that could fry delicate electronics before they cross a fraction of the void. The sheer distance between stars is the first, most humbling barrier. Alpha Centauri, our closest stellar neighbor, lies 4.37 light-years away, over 25 trillion miles. For context, if Earth were a marble in New York, Alpha Centauri would be another marble in Los Angeles. Traditional rockets, even with today's most advanced propulsion, would take tens of thousands of years to make that journey. Breakthrough Starshot's laser-driven nanocraft offer a tantalizing shortcut, but scaling this technology for human travel is another universe of challenges. Humans aren't microchips. We require oxygen, food, and protection from radiation demands that turn interstellar vessels into sprawling, heavy arcs. Then there's the invisible menace, cosmic radiation. Outside Earth's protective magnetosphere, space is flooded with high-energy particles from supernova and black holes. On a multi-decade voyage, exposure would exceed lifetime safety limits within months, increasing cancer risks and potentially damaging vital organs. Shielding solutions like magnetic force fields or thick layers of water add immense weight, further complicating propulsion. Even if we solve propulsion and radiation, there's the psychological toll. Imagine spending a lifetime or generations confined to a metal hull with no guarantee of success. The closest analogy is submarine crews, but their missions last months, not centuries. Yet the dream persists. Alternative concepts like nuclear pulse propulsion or antimatter engines flirt with theoretical feasibility but remain shackled by physics and funding. Some propose generational ships where descendants of the original crew finish the journey, raising ethical questions about consent and survival in deep space. Others bank on cryogenic hibernation, freezing astronauts until technology or arrival renders the voyage bearable. Each idea is a gamble, trading one set of problems for another. The truth, we're not ready, not yet. But the pursuit itself is transformative. Every technical hurdle forces innovation, from energy-efficient life support to radiation-resistant materials with spin-off benefits for Earth. And the philosophical shift is just as profound, accepting that interstellar travel isn't about one lifetime but many. It's a project for civilizations, not individuals. Whether we reach the stars in a century or a millennium, the first step isn't building a ship, it's changing how we see our place in the cosmos. The stars aren't just points of light, they're destinations waiting for us to grow into the kind of species that can reach them. From dark energy's relentless push to black holes' quantum secrets, these cosmic revelations prove the universe is far stranger than we ever dreamed. Each discovery peels back another layer of mystery, reminding us how much we have yet to learn. Just a century ago, we thought the Milky Way was the entire cosmos. Now we know it's one of trillions of galaxies, each teeming with planets, pulsars, and phenomena that defy imagination. And with every breakthrough, the universe seems to double down on its unpredictability, tossing us curveballs like dark matter's invisible grip or the eerie fine-tuning of the laws of physics. Consider this: the atoms in your body were forged in the hearts of dying stars, scattered across space by supernova, and woven into the fabric of Earth over billions of years. You're not just observing the cosmos, you're a living, breathing piece of it. That's the real magic of these discoveries. They're not just abstract equations or distant phenomena. They're threads connecting us to everything, from the quantum foam of space-time to the vast, accelerating expanse of the universe itself. The best part, we're only scratching the surface. New telescopes like the James Webb Space Telescope and the upcoming Vera-C Rubin Observatory are poised to reveal galaxies older than we've ever seen, exoplanets with atmospheres ripe for life, and perhaps even answers to dark energy's enigma. Gravitational wave detectors are tuning into the universe's hidden symphony, listening for collisions between neutron stars or the echoes of cosmic strings. And quantum computers might one day simulate the birth of the universe itself, unlocking secrets buried since the first picosecond of the Big Bang. But here's the thing, you don't need a PhD or a spacesuit to be part of this adventure. Every time you look up at the night sky, you're participating in the oldest human tradition, wonder. Whether it's tracking a meteor shower, spotting Jupiter's moons with binoculars, or just marveling at the scale of it all, that curiosity is what drives discovery forward. The universe isn't just for scientists, it's for anyone willing to ask, what's out there? So, what's next? Maybe we'll find microbial life on Mars or Europa. Maybe we'll crack the code of quantum gravity or detect signs of an alien civilization. Or maybe the biggest revelation is still something no one's even thought to question yet. One thing's certain, the cosmos isn't done surprising us. If you've enjoyed this journey through the universe's greatest mysteries, hit like, subscribe, and let us know in the comments what cosmic question keeps you up at night. The next chapter of Discovery is being written right now, and you've got a front row seat. Stay curious.